In this video, we'll discuss similarity. Now, when we're talking about similarity, we're looking at similar objects and shapes where the corresponding angles are equal in measure and the corresponding sides have the same proportional measurement. That proportion we call the scale factor, and that's the ratio of one object's length to the other object's length, and all sides have to have that scale factor. Now, it's important to recognize that if objects are congruent, they are also similar because they have a scale factor of 1 to 1. So let's look at these three triangles and say, are any of them similar? And here, I want to match up the sides and say, do they follow the same scale factor? When I look at A to B, I can look at each of these sides, CA to VP, AL to PZ, and CL to VZ, and see that's a 2 to 1 scale factor. But if I do A to C, that side HJ doesn't match up with CL in the same way. And if I compare B to C, that side VZ doesn't match up with HJ. So the only set of similar shapes I have in this image are shape A and shape B. Now, if I want to determine measurements, I'm going to take for angle measures, set the angle measures equal to one another and solve for what may be unknown in my image. For side lengths, I need to use that scale factor and set up a proportion to solve for that unknown. So let's look at an example. Say that I create a funny face on a piece of paper and I want to blow it up onto a poster. If the original face was on 8 by 12 paper and I want to make the poster be 4 times each of those dimensions, how big should my poster be? So let's start by labeling what we know. We know the small face is 8 by 12. And I can start by first saying that my scale factor then has to also be 4 to 1. And that's the big to the small. So from my poster to my paper. So I can use that scale factor then to find the dimensions of the big poster. So let's start with the width. I don't know it right now, but I can use that scale factor and set up a proportion where I can say the 4 to 1 is my scale factor. That's the big to the small. So the big poster width to the paper width. I cross multiply and I'm going to get that the width should be 32 inches. Now I can do the same thing for the height of the poster or the length of the poster. I don't know it, but I can use my scale factor and say, well, that's 4 to 1 equals h to 12 inches from the big poster to the small paper. Again, I cross multiply and I would get 48 inches for that height, and that would tell me that my poster would need to be 32 inches by 48 inches. Now we can also talk about similarities specifically for triangles, and there's several methods that we will use, one of them being angle-angle. And in this, if we know two of the angles, corresponding angles are congruent, then we know that the triangles have to be similar. And we only have to know two, because the third one automatically will be congruent as well. So here I have in this image two triangles, one separated by the parallel lines. Because we're told that ED is parallel to CB or BC. And we know that the corresponding angles of parallel lines are congruent. So in this case, what that means is that angle ADE is congruent to angle ABC, and then AED is congruent to ACB. And so by using angle-angle, I can say triangle ABC, that's my large triangle, is similar to triangle A, because I got to match up my angles, and then the corresponding angle to B is angle D, and the corresponding angle to C is angle E. Another method I can use is side angle side. And here I know that I have two sets of corresponding sides of one triangle are proportional to another triangle, and the included angles are congruent. That's what makes side angle side. The big thing to pay attention to is when you have that included angle, sometimes you may have to check the order of those sides to figure out where the proportion falls. So you do need to check it both ways. So here I have an image and I want to know what are the two similar triangles. So I can see that I have the included angles as marked, and now what I'm going to do is compare the sides and figure out, do I have one sets that have the same scale factor. So first thing I would try is I'd say, okay, I like 6 to 3, that's easy to do, so let me check the other one. So that I know 6 to 3 is a 2 to 1 ratio, so let's check the other two sides. Well, that's 5 to 2.5, which is also 2 to 1, which that tells me then that the triangles have proportional sides. Therefore, it must be similar by side angle side. So now we just need to match up those pieces. So the corresponding angle to J is actually going to be G because of how these sides are marked. And then H would be corresponding to H, and then K would correspond with K. So triangle JHF is similar to triangle GHK. So we do need to pay attention to that order as we do these problems. The third option you can have is side, side, side. And here, all three sets of corresponding sides have the same scale factor. And if that's the case, we know they must be similar. And also remember, it could be a 1-to-1. So all of our congruent triangles are also similar triangles. So here, we have two triangles, and we can match up the corresponding sides. And we want to check those scale factors. In this case, we know that QR to ML has a 4-to-12 or 1-to-3 ratio. RP to LN is a 2-to-6 or, again, a 1-to-3 ratio or scale factor. And then QP to MN has that 3-to-9, which is also a 1-to-3 scale factor. Therefore, they all have the same scale factor. All the sides have the same proportion. Therefore, it is by side, 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 QR or QPR would be similar to triangle MNL. Now we can apply these similar triangles to help us solve larger problems. And here's an example of one of those. Let's say that Ben is 6 feet tall and he wants to find the height of a tree his parents planted when he was born. When he stands, he casts a 4-foot shadow. Ben then measures the tree's shadow and finds it is 12 feet. How tall is the tree now? So let's draw a picture to help us out. Here we have Ben in his shadow, the tree in his shadow, and we can see the sun shining down to help create those shadows. Let's label the pieces we know. We know that the shadow of Ben is 4 feet, he's 6 feet tall, and we know the shadow of the tree is 12 feet. And if we look at what's created here, we actually are going to be using similar triangles because we're assuming that they're both vertical to the ground. So we've got that right angle that we're thinking about being perpendicular. So we've got two similar triangles we can use, and now we can calculate the height of our tree. So let's set up a proportion. And let's go from small to big equals small to big. So we've got the bottom side to the bottom side equals the top side, or the right leg to the right leg. Now we can cross multiply, and we're going to get that 4 feet equals the 72 feet squared, because feet times feet. Now we're going to divide both sides by the 4 feet, and when we do that, feet squared divided by feet will leave me just with the 18 feet. So what that tells us is the tree was 18 feet tall at that point. Now let's talk about one last topic that comes up with similar triangles, which is the geometric mean. And if you remember, a geometric sequence is where we're multiplying the same factor each time from one number to the next. And so if we have 3 of those numbers in the geometric sequence, we know that B will represent the geometric sequence if A over B equals B over C. So let's look at an example to help us understand what's going on. Say we want to determine the geometric mean of 4 and 9. You're like, well, that's kind of weird, but there's got to be some number that we multiply to get in between. So we're looking at that sequence of 4, that number we don't know yet, and 9. So let's try using our proportion here. So we can say that A is 4, B is X because we don't know it, and then C is 9. So we have 4 over X equals X over 9. When we cross multiply here, we're going to end up with X squared equals 36. We're going to take the square root of both sides, and that will leave us with only the positive value because we're dealing with, in this case, just measurements. So that'll give us a positive 6. So when we think about what that means, if we substitute in 6, we have 4 over 6 equals 6 over 9. When simplified, they're both 2/3. So this is the actual value that we would say. It's 4, 6, 9 in the geometric sequence. And you're like, well, okay, well, what's that multiplying factor? Well, 4 times 3 halves gives me 6. 6 times 3 halves will give me 9. So it's a factor of 3 halves that gets me from one term to the next. Now, where does this apply into similar triangles? We have a unique case that if we draw the altitude of a right triangle constructed from that right angle to the opposite side, then we know there are multiple geometric mean relationships that exist within this image. Specifically, the most common one we will use is saying that CB, this little segment of the hypotenuse, over CA, that altitude, will equal CA over the rest of the hypotenuse, in this case CD. So let's look at an example of how this can be used. So say we want to know what is the hypotenuse dB if we know that CB is 6 and AC is 18. So let's put in the parts we have. We know that CB is 6, CA is 18. What we don't know is the entire length. But to think about, what do we need to make up this entire length? We need to know DC, and that's the part we don't know right now. So the entire length would be that unknown part of DC plus 6 units. So we then look and say, well, we do have a relationship among these three parts, which is this geometric mean. So we can say that CB over the altitude, CA, equals CA over the other part of the hypotenuse, CD. I can substitute in the values I have, which would be 6 over 18 equals 18 over CD. I cross multiply here, and then I can divide both sides by 6 to get 54. Now that I have that smaller part, I can then use segment addition postulate to create the entire length of the hypotenuse, dB. Because I know that dB has to equal DC plus CB. So that's 54 plus 6, which means that the hypotenuse of this triangle would be 60.